For number 21, we're asked to evaluate the cosine of 2 times a. There are 3 trig identities for the cosine of 2a, so I just chose to use the first one of them. You can use any of the 3 and they shall give you the same result. So I'm using cosine squared of a minus sine squared of a. Now all we have to do is look at our picture for angle A and find the cosine and square it, find the sine and square it, and then subtract. So let's take a look at our picture for angle A. The sine of angle A is negative 12/13, and the cosine of angle A is positive 5/13. So 5/13 squared minus negative 12/13 squared is 25/169 minus 144/169. Don't forget that when you're squaring a negative number, you have to square first and get a positive result and then subtract. And then the result from there is negative 119/169. In 22, we're asked for the value of tangent of 2 times c. And the double angle identity for tangent is 2 times the tangent of angle C divided by 1 minus the tangent squared of angle C. Now we just have to make some substitutions. So we're going to find the value of tangent C and replace it in this template. So let's take a look at our picture for angle C. And in angle C, the tangent of angle C is equal to negative 3/4. 2 times negative 3/4 is negative 3/2, and then negative 3/4 squared is 9/16. So now what we have is negative 3/2 divided by 16/16 minus 9/16 is negative 7/16. So that's negative 3/2 divided by negative 7/16, which means times 16 over negative 7. We can cancel some common factors, and that will give us a result of positive 24/7. All right, in the next section, we are proving trigonometric identities. Remember that when you prove a trigonometric identity, you're going to start with a statement that something is equal to itself, which is a demonstration of the reflexive property. So we're going to start with sine of 90 minus theta is equal to the sine of 90 minus theta. A reader of the proof would find that intuitively obvious, and then they should be able to see all of the steps that are taken from there. So on the right side, we're going to transform this until it turns into a cosine of theta. Now using the sine of a minus b is the sine of a times the cosine of b minus the cosine of a times the sine of b. As an identity, we can re-express the sine of 90 minus theta. And now the sine of 90 degrees is 1, and the cosine of 90 degrees is 0. And 1 times the cosine of theta is the cosine of theta, and 0 times the sine of theta is 0, and cosine of theta minus 0 is the cosine of theta. Now I'm just going to bring down the sine of 90 minus theta. On the left side, you don't have to write it in every single step. And you'll notice that our last step says what we were trying to prove. I'm going to write QED, but you do not have to. In number 24, we're asked to prove that the secant of 180 minus theta is equal to negative secant of theta. So I'm going to start with a statement that the secant of 180 minus theta is equal to the secant of 180 minus theta. We don't have an angle difference identity for secant, but we do have one for cosine. So I'm going to re-express secant of 180 minus theta as 1 divided by the cosine of 180 minus theta. And the cosine of 180 minus theta is the cosine of 180 times the cosine of theta plus the sine of 180 times the sine of theta. That's using the angle difference identity for cosine. And the cosine of 180 degrees is -1. And the sine of 180 degrees is 0. And so we wind up with -1 over the cosine of theta, because 0 times sine of theta is 0. And -1 over the cosine of theta is negative secant of theta. And now I'm just going to bring down what we had on the left side, secant of 180 minus theta, and we are done with that proof. In number 25, I'm going to start with a statement that the cosine of theta times the cotangent of theta plus the sine of theta is equal to itself. And then on the right, I'm going to transform. And since I'm not really quite sure what else to do, I'm going to change any trigonometric functions that are not sine or cosine into sines or cosines. So I'm going to leave my cosine alone, or I'm just going to put it over 1 to express it as a fraction. And then I'm going to re-express cotangent of theta as cosine of theta divided by the sine of theta using the quotient identity. And then I'm going to re-express the sine of theta as the sine of theta over 1. So now we have a bunch of fractions here that we can work with. And the cosine of theta times the cosine of theta is the cosine squared of theta over the sine of theta is the result for that first fraction. And then if we're going to add fractions, we're going to need to have a common denominator. So I'm going to multiply the second fraction that we're adding by sine of theta divided by sine of theta, a clever form of 1 that will give us a common denominator. So that gives us sine squared of theta divided by the sine of theta. And now we have a common denominator, so our fractions can be added together. And when we add fractions, we add the numerators together and keep the denominator. And it turns out that the cosine squared of theta plus the sine squared of theta is equal to 1 due to the Pythagorean identity. And 1 divided by the sine of theta is the cosecant of theta, which is what we were aiming for. So I'm going to bring down the other side of the equation here. Cosine of theta times the cotangent of theta plus the sine of theta is equal to cosecant of theta. And we are done with that proof. In number 26, I'll start with a statement that the cosine squared of angle A plus the tangent squared of A times the cosine squared of A is equal to itself. So that would be the cosine squared of A plus the tangent squared of A times the cosine squared of A. And similar to our previous, I'm going to take any functions that were not cosines or sines and re-express them as cosines or sines. Tangent squared of A is the same as sine squared of A divided by the cosine squared of A. That's just the square of the quotient identity. And then we can multiply that by cosine squared of A. If you prefer, you can write that over 1. Now I'm going to grab my cancellation pen, cancel our common factors, and we are left with cosine squared of A plus the sine squared of A. And that is a Pythagorean identity. That is 1. So now I'm just going to bring down the other side of the identity that we tried to prove here. And now we are done with that proof. In number 27, I'll start with the secant of theta minus the cosine of theta is equal to the secant of theta minus the cosine of theta. So, since I don't know what else to do, I'm going to change any functions that are not sines and cosines into sines and cosines. So secant of theta is 1 divided by the cosine of theta. And then we're going to subtract the cosine of theta, which I'm going to write over 1. And then let's use a clever form of 1 to give ourselves a common denominator. And that will give us 1 minus the cosine squared of theta divided by the cosine of theta. Right, because now we have a common denominator of cosine theta, and we can just subtract the numerators. And now let's remember something. So I'm going to write a little thought bubble up here at the top. Remember that the sine squared of theta plus the cosine squared of theta, I can't write, sine squared of theta plus the cosine squared of theta is equal to 1, which means that sine squared of theta is equal to 1 minus cosine squared of theta, right? We can just move the cosine squared to the other side by subtraction. So that means that the 1 minus cosine squared in our proof can be replaced by sine squared of theta. Now let's take a look at our target. Our target is sine of theta times the tangent of theta. So I'm just going to separate out here 1 sine of theta times sine of theta divided by the cosine of theta, and that is equal to the sine of theta times the tangent of theta. And we can just bring down the other side and write QED. I'm running out of room here, but let's just imagine that I brought this down to the same side of the equation there. All right, one more to do on this page. Sine of theta plus cosine of theta, the quantity squared, minus 1 is equal to the sine of 2 theta. So I'm going to start with the sine of theta plus the cosine of theta squared minus 1 is equal to the sine of theta plus the cosine of theta squared minus 1. And when we square a binomial, remember that's multiplying the binomial times itself. So that's sine of theta plus cosine of theta times the sine of theta plus the cosine of theta. And let's bring down that minus 1. And now we can FOIL. So that gives us sine squared of theta plus, and the inners would be, or rather the outers would be sine of theta times the cosine of theta. And the outer product would be sine of theta times the cosine of theta also. And then the last product would be cosine squared of theta, and that'll bring down that minus 1. So now reordering some things, we have one term that is the sine squared of theta, and a second term that is cosine squared of theta. And then we have 2 of these, so that's 2 times the sine of theta times the cosine of theta, minus 1. Remember that the sine squared of theta plus the cosine squared of theta is equal to 1. So now we have 1 plus 2 times the sine of theta times the cosine of theta minus 1. And combining like terms, that is just 2 times the sine of theta times the cosine of theta. And that just so happens to be the double angle identity for sine. So that is the sine of 2 theta. Let's bring down the other side of the equation, and that is sine of theta plus the cosine of theta squared minus 1, and now we've proven that identity. All right, on the next page, proving that the tangent of the opposite of theta is equal to the opposite of the tangent of theta. Let's start with tangent of the opposite of theta is equal to the tangent of the opposite of theta. And now we can transform the right. The opposite of theta is the same as 0 minus theta. Now we can use an identity for tangent of a minus b. So tangent of a minus b is tangent a minus tangent b divided by 1 plus tangent squared tangent a, which is 0, times the tangent of b, which is theta. All right, now tangent of 0 is 0, So now we're going to replace all those tangent of zeros with 0. So 0 times theta is 0. That means that the numerator simplifies to negative tangent of theta. The denominator simplifies to 1. So that is equal to negative tangent of theta. And we can just bring down the other side of the equation. So tangent of the opposite of theta is equal to tangent of theta. And now we are done with that proof. For number 30, and this one's our last one, we have the secant of the opposite of theta is equal to the secant of theta. So for this one, let's start with the secant of the opposite of theta is equal to itself. Remember, we're always starting the proof with the reflexive property. And then I'm going to re-express the secant of the opposite of theta as 1 divided by the cosine of the opposite of theta. And cosine of the opposite of theta is the same as cosine of 0 minus theta. And cosine of 0 minus theta is cosine 0 cosine theta plus sine of 0 sine of theta. And cosine of 0 is 1. And sine of 0 is 0. And so simplifying the denominator there, we get just cosine. And 1 divided by cosine is secant. So bringing down the other side of the equation here, we have secant of the opposite of theta is equal to secant of theta. And we are done with that proof. And I believe that's the last one in the review.